Welcome to this lecture. So far we have looked at some basic aspects of real time operating systems, and then we said that real time scheduler, task scheduler is a vital part of the real time operating system, and we have been looking at some of the real time task scheduling algorithms. The event driven schedulers are sophisticated schedulers compared to the clock driven schedulers, and rate monotonic algorithm for being useful in different practical situations. In the last lecture we were looking at the deadline monotonic algorithm, where the task period and deadline are not identical. Today we will look at some more generalizations before starting to discuss about some of the issues. So far we have simplified, assuming that tasks are independent and so on, they do not share resources. So, that under these simplified assumptions we have been discussing so far. So, that assumption we will relax after discussing the rate monotonic algorithm generalizations. So, let us get started. One important thing that occurs frequently in designing and implementing real time applications is that some of the tasks which are very critical tasks may not have the highest repetition rate or the lowest period. There may be other tasks which are less critical or maybe non-critical, which have high repetition rate, and due to the rate monotonic priority assignment, which says that assign highest priority to the task that has the highest frequency of repetition or the lowest period. By that assignment, even a very critical task may get assigned a low priority, and therefore, whenever a low priority task, low critical task gets delayed, the high critical task may miss its deadline. One simple solution to this is to just raise the priority of the critical task, but then that makes all the results that we discussed, Liu, Lehoczky's, etc., become inapplicable. Now, let us look at how to handle this situation. So, there are often situations where the task criticalities are different from the task priorities, and if we simply adjust the priorities and violate the rate monotonic priority assignment, then the results that we so far had on rate monotonic analysis would not hold. To overcome this situation, a solution was proposed by Shah and Rajkumar in 1989. The name of the technique is period transformation technique. Let us look at the period transformation technique. The main idea here is very simple. A critical task having high period, long period, is split into many smaller subtasks, depending on to what extent we want to raise its priority. If we want to really raise its priority, then we split it into many subtasks such that it becomes, the new period becomes lower than the other tasks. Now, let us assume that we have a task T I, and we know that it is a highly critical task, and then we split it into k subtasks. So, the execution time for each of these subtasks become E I by k, where E I is the execution time for the task T I and D I is the deadline, and the deadline for each of these subtasks becomes D I by k. But one thing we need to understand is that we are not changing anything in the code, the task, etc. This we are doing only for helping us with our analysis without violating the rate monotonic constraint, so that we can apply the rate monotonic analysis techniques that we have discussed so far. We are just virtually considering the task to be split into k subtasks, and then the priority of this task increases, and but the total execution time of all the subtasks together add up to the actual time. Just to give an example, let us say we have task T 1 whose period is 20 millisecond, requires 5 millisecond execution time. The task T 2 requires 8 millisecond execution time, but has a period 30 millisecond. In the rate monotonic priority assignment, T 1 will be assigned highest priority and T 2 a lower priority. Now, assume that T 2 is a critical task and T 1 is not so critical. So, we want that even if T 1 gets delayed due to some reason, T 2 should not miss its deadline. In that case, we split T 2 virtually into two subtasks, T 2 A we can consider it to be just one subtask which has high repetition rate, but low execution time. So, that means we have split T 2 into T 2 A whose execution time is 4 and deadline is 15 millisecond. So, the overall task characteristics has not changed, it is 8 millisecond execution time every 30 millisecond. Only thing is that for our analysis purposes, we have assigned a priority to the task T 2 that is higher than T 1, and we have considered that the execution time is 4 and deadline is 15. And with this assumption, we can still apply the rate monotonic analysis results. Now, let us look at another issue, which is handling aperiodic and sporadic tasks. In the rate monotonic priority assignment, we had so far looked at only periodic tasks, and based on their period, we assign priorities during the design time. But what if there are aperiodic and sporadic tasks? The aperiodic and sporadic tasks, they do not occur periodically, rather they occur randomly. We cannot really approximate them to be periodic tasks with some period, because there can be bursts of sporadic tasks, and once we get bursts of this task, if we have assigned higher priority to these tasks, then the tasks that are lower than this priority would miss deadlines. And also, when the sporadic or aperiodic tasks do not occur, then we are unnecessarily underloading the system. to overcome this situation, the periodic server technique has been proposed. Let us look at the periodic server. Before that, let us look at some aspects of the sporadic tasks. So, there are two types of sporadic tasks. Some are high priority. For example, an emergency event like let us say there is a fire detection reported and a task needs to be started to report fire conditions and also to start the water sprinklers. So, this is a very random event, occurs very rarely, but then this is a high priority event, it should not get delayed. But then there are non-critical tasks which can be sporadic. For example, let us say logging of the results. So, this also once in a while need to log the results, and such non-critical tasks like logging results etc., they can accommodate some delay in execution, they can tolerate long response times. So, during a overload situation, the background jobs can be deferred, but for high priority tasks like emergency events, we should be able to execute in the rate monotonic framework and should be able to accord high priority to these tasks, so that these meet their deadline. A very obvious way is to convert these high priority sporadic tasks into periodic tasks. For example, if it is a fire alarm handling task, then we find out what is the maximum deadline that will be permitted in handling this task, and then we consider it to be a periodic tasks with the period is equal to the deadline that is acceptable. But then there may be many types of such tasks, many tasks which occur very rarely, but are high priority, and also if we use the simple solution, then there can be a design problem that we have the system that is highly underloaded. Can we handle these sporadic tasks in a better way? Before looking at that, the periodic server technique, let us look at first handling the non-critical tasks, which are we call as background tasks. We can easily handle the background tasks in the rate monotonic framework by keeping the real time tasks in a queue and apply the rate monotonic scheduling on them. And whenever there are no real time tasks, high priority tasks to execute, the CPU idle, and then we have another FIFO scheduler where the aperiodic tasks have been queued. It just takes from the queue in a first in first out and executes these low priority tasks, and see that there is no guarantee when will these tasks get executed, but as and when the CPU becomes available, the other high priority tasks are not executing, the FIFO scheduler becomes active and starts executing the aperiodic tasks, and as soon as periodic tasks come, the aperiodic tasks are preempted. So, handling background tasks is simple. In addition to the rate monotonic scheduler, we use a FIFO scheduler for handling the aperiodic tasks. Now, let us see how to handle high priority sporadic tasks more efficiently than just considering each high priority sporadic task as a periodic task with period is equal to the acceptable deadline. First, let us look at the periodic server. A periodic server is a high priority task and it handles multiple sporadic tasks that have deadlines associated with them, and the period of this periodic server is decided based on the different sporadic tasks that it handles. The assumption here is that the sporadic tasks occur very rarely, for example, fire handling events and so on, and therefore, a single periodic server can handle multiple sporadic tasks, because at any time it is expected that only one or so will occur. But then we can also have a design where there are multiple periodic servers, where we have from design considerations we have clubbed different sporadic tasks with similar characteristics into and assign them to one periodic server, and another periodic server handles tasks with different similar characteristics. Considering the practical importance of the periodic servers, lot of developments have taken place in the periodic server technique. There are static servers and dynamic servers. The static servers, as the name says, they have static priorities. The dynamic servers have dynamic priorities. And then we have the slack stealer, which we had already seen that whenever there is a lax time or a slack time, the scheduler like a FIFO scheduler gets active and executes any pending background jobs. There are several types of static servers: the polling server, deferrable server, priority exchange and sporadic server. The sporadic server is the one which is supported by the POSIX real time standard. The polling server is possibly the simplest among them, and we will discuss the polling server in the next few minutes. The other ones, the deferrable server, priority exchange and the sporadic servers, are simple improvements over the polling server. So, we will look at only the basic concepts here, and if necessary you can read the text book that is we are referring for the other types of static servers. The polling server is a periodic task, and it is assigned a priority according to the rate monotonic algorithm, and the period of this polling server is decided based on the characteristics of the periodic tasks, the sporadic tasks it handles. But then compared to a simple server, periodic server which just keeps on repeating, and even if there is CPU, there is no sporadic task, it just idles the CPU time. A polling server suspends itself, so that the other tasks can execute. But then if there are sporadic tasks during an invocation of the polling server, because the polling server is invoked at time T s, which is the period of repetition for the polling server. during any invocation, if there is a sporadic task, then it serves up to estime. It should be clear that the polling server has a period Ps and execution time Es. So, during the rate monotonic analysis, we consider the utilization due to the polling server to be Es by Ps. Now, the schedulability analysis become easy when we handle sporadic tasks through a polling server. We just consider the polling server to be a task with execution time Es and period Ps. But then, since on every occurrence there may not be enough sporadic tasks to run, the schedulability of the other tasks which are lower priority than the polling server become less. Now, let us look at the schedulability analysis, how to perform. We assume that the execution time is Cs or Es, okay, it is the notation used here is Cs, required every Ps time. So, the utilization due to the polling server is Cs by Ps. For all other tasks, it is sigma I equal to 1 to n Ci by Pi, and therefore, the total utilization for all tasks including the polling server is given by the left hand side expression, and if there are n other tasks and one polling server, then we have total n plus 1 tasks, and in the Liu-Lehoczky's the Liu-Leyland's formula, we just use n plus 1 into 2 to the power 1 by n plus 1 minus 1. So, as long as this is satisfied, then along with the polling server, the other tasks will become schedulable. But then how do we fix the deadline or given the deadline of the sporadic tasks, how do we fix the period of the polling server? We use a very common intuition here that the worst case for a sporadic event occurs just after, if it occurs just after the time period of a polling server is over. So, the polling server was getting this slot for execution, but towards the end of it, just before it completes, the sporadic task occurred. Now, the sporadic task cannot be served here in this time slot, because it has occurred towards the end of this. It can only be taken up in the next slot that the polling server gets, which is after Ps time. But then the polling server may not get the time at the time instance 0 from this period. It may not immediately get served. So, it will get served by the rate monotonic scheduler before its period Ps. So, it can be anywhere here, and therefore, if the sporadic task requires a execution time which is Ca and Ca is less than Cs, then it can be served in one instance by the polling server. Therefore, in this worst case, the deadline must be greater than 2 Ps, because 1 Ps it just missed here. So, only it can be taken over in the next period where it gets a time slot for execution, but then there is no guarantee that it will immediately be taken up. It may be taken up towards the end also, end of the period. So, the deadline must be greater than 2 PS, or we can fix PS as less than half the deadline. Let me repeat that. To assign the period to the polling server, we look at all the sporadic tasks it needs to serve. We find the task that has the lowest deadline, and then we take half of that, and the polling server should have a period which is less than half the deadline of the sporadic task having the shortest deadline. Since we are running out of time now, we will stop here and we will look at few more issues before we look at the resource sharing among real time tasks. Thank you.